Oh, thank you. Yeah, I did. I remembered this time. Okay, so if no homework questions, then let's go ahead and jump into this practice thing. And we're just going to start at the beginning and just work our way all the way down. Let's see, how do I want to do this? I guess I could just write straight on this. Let's do it that way. So our first question here. Find the sum to the series. It's the series n equals 3 to infinity of 1 over 4 to the n. So you just have to be careful with ones like this. This is a geometric series. I think I've stressed this a lot, but it's never going to ask you to find the sum unless it's a geometric series. It's geometric because it's almost in one of those formats that we have for geometric series. Remember, we have two different versions. So we have this one where the index starts at 0 to infinity, AR to the n. And then the same thing we could write like this, where the index starts at 1 to infinity. And then it's AR to the n minus 1. So it's just shifting the index over once. This example, though, has our index starting at 3, so we're going to have to do some weird stuff. And there's two ways to do this one. One way would just be to write out the terms and see what you get. So plug 3 in first. We have 1 over 4 cubed, which I think is 1 over 81. I might be wrong about that. No, that's not right. 1 over 64. Plus, and it'd be 1 over 4 to the 4th, and 4 to the 4th is something. 256. So then the next one would be 1 over 256 plus, and I'm just going to dot it, right? So it would just go on forever and ever and ever. Every single time we'd be multiplying by a 1/4. So if you just look at this series as a geometric series, you can pick out the A and you can pick out the R. The A is always going to be whatever the first term is. So that 1 over 64 is going to be the A. The R is that ratio that you multiply by every single time to get to the next term. To get from 1 over 64 to 1 over 256, we're multiplying by a value 1/4. So that gets us the A and that gets us the R. And then remember, for geometric series, the sum always comes out to be A over 1 minus R. As long as the R is less than 1, which is what we have here. All right, there is another way to do this question, and that's by shifting the index. So instead, we could start back over n equals 3 to infinity. I'm going to think about this as being 1/4 to the n, like that, instead of the n just being on the 4 in the denominator. But what we can do is that we can shift the index over until it gets to either 1 or it gets to 0. Let's just get it to 1. So instead of starting at 3, we're going to start it at 1 and going to infinity. That 1/4 stays, but now this n has to change. If I plug 1 into the exponent, it still has to be the same thing as plugging 3 into the exponent. So the only way to do that is to have this numerator be n plus 2. Because if I plug 1 in, I get 3, which is technically what the first index value should be. If I plug 2 in, I get 4, which is what the next index value should be, and so on and so forth. Now, this isn't quite in one of the formats yet, but I can force it to be one of the formats by pulling some stuff out of the exponents. So leaving the index alone, still going from 1 to infinity, I need this to really be an exponent n minus 1. So to get from n plus 2 to n minus 1, I have to pull out 3 of them. So I'm going to pull out a 1/4 to the 3, and then that's going to leave me with a 1/4 to the n minus 1. Then what we have, still the sum, n going from 1 to infinity, and then 1/4 cubed, that's the 1 over 64. All right, and now it's written in the format that we have with the definition for geometric series. The A constant out in front, and then the R value to the n minus 1. So you could have gotten it either way, by writing out the first terms and figuring out what the a and the r value are that way, or by rewriting your series into one of the definitions that we have for geometric series. The sum itself, right, that a over 1 minus r, is going to be a, the 1 over 64, if I can type, divided by 1 minus the r, which is 1/4. All right, and then you just type this into the calculator to figure what this comes out to be. I'll do that. So 1 over 64, I'm going to take whatever that is and divide that by 1 minus 1/4. We get some awful decimal, but if I switch this back over, oops. If I switch this back over to a fraction, 1 over 48. So that should be the answer for part A here. The sum of the series 1/4 to the n starting at 3 comes out to be 1 over 48. So is that one all right? Does that make sense to everybody? Any questions about that one? All right, part B. So part B is asking the same thing. It's still asking us to find the sum of this series. So to find the sum of this series, we have to rewrite it into that geometric form because it is not in geometric form as it stands now. So let's fiddle with it. Let's write this. It's still going to be the sum in going from 0 to infinity. One trick that we have for geometric series is that if you have two terms up top and just a single term in the bottom, you can divide each of those by that term in the bottom. So it's going to be 2 to the n plus 1 divided by 4 to the n. I'll just go ahead and write that as is for now. Oops, sorry, wrong button. 2 to the n plus 1 divided by 4 to the n. Plus, oh crap, that's not how that's supposed to look either. Well, I'm just going to have to rewrite it. This is the problem with working in Word, right? It's like you either get it one way or the other. Either you can actually read it, because my handwriting is so bad the other way, or you have to deal with me typing in stuff wrong. Okay, great. So that plus, and then the other thing would just be that 3 divided by 4 to the n. Remember that we have the addition rule for sums, so I can break this up into two separate infinite sums. I'm not actually going to do that, but that's really what we're doing behind the scenes. I'll just leave it as one sum for now, and we need to rewrite each of these so that it's in that AR to the n format. For this first one, 2 to the n plus 1 divided by 4 to the n, what I can do is I can pull one of these 2's out and rewrite that numerator as 2 to the 1 times 2 to the n, all divided by 4 to the n. The reason I want to do that is now that 2 I can just think about as being out in front, and then because both the 2 to the n and the 4 to the n have the same exponent, I can combine those together and just write 2 over 4 all to the n. We're going to do something similar to the other one. I'm just going to pull that 3 out because it's already to the 1, and then think about the 1/4 that would be left over to the n. Okay, so just to simplify down the first thing now. Still n going from 0 to infinity. This is the last line we'll write here. We're going to pull the 2 out to the front, and then we have 2 over 4, which is the same thing as 1/2 to the n. That plus the other infinite series, 3 times 1/4 to the n. Now each of these is written in that AR to the n format. So that means that the sum is just going to be the two sums added together. So the first series, A over 1 minus R, is going to be 2 over 1 minus 1/2, plus the second series, A over 1 minus R, is going to be 3 over 1 minus 1/4. Okay, and then you just type all this into the calculator to get an answer here. I'm going to try and do it in my head. So this comes out to be 4, I think, plus 3/4, 12, 16? Does that look right? Somebody double check my math there. That can't be right. No, I messed it up somewhere. I think this is a 4. I think it comes out to be 8. 4 plus 4, 8. That looks a lot better. So this infinite sum, if you were to take all of the terms all the way to infinity and add them all together, adds up to be exactly 8. All right, good. Geometric series. Any last questions about those? Okay, cool. Moving on. Question 2. Show that the series, the infinite sum n equals 1 to infinity 1 over n to the 4th, converges by comparing it to the improper integral 1 to infinity 1 over x to the 4th dx. So this one's kind of giving it away how they want you to do this one. They're going ahead and telling you to do the integral test. Know that we can do the integral test because it meets those prerequisites. We have to have the sequence values as a function be continuous, at least on the interval that we care about from 1 to infinity, which it is. It has to be decreasing, which again from 1 to infinity it is decreasing, and they always have to be positive. And again from 1 to infinity these are all positive. So we are allowed to do the integral test. So we just do it. All right, what we do is we take the integral here and we calculate that. So this has an antiderivative of, let's see, it'd be negative 1/5 x to the negative 5th. That we're going to evaluate between 1 and infinity. Great. Another way of thinking about this, because that's a little bit hard to imagine what that's going to come out to be, we could think of it as just negative 1 over 5x to the 5th like this. It might be a little bit easier to think about it that way when we're plugging infinity in. All right, if I do plug infinity into this, then this x is going to blow up to infinity, which is just going to make the whole thing go to 0. Minus plugging 1 into the antiderivative, which is going to give us negative 1/5. So this integral comes out to be positive 1/5. Now, I don't care super much about what that integral comes out to be, as long as it comes out to be a number. If this diverged or goes to infinity compared to it coming to a number, it tells us the two different things. So, because this integral converged to a number, let's see, since, oh geez, come on word, you can do it. Since the, oh geez, forget it. Since the integral converged to a number, then the series will also converge to a number. And then remember, it's the other way around too. If the integral diverges, that means that this series also diverges. All right, so that's the integral test. If you can rewrite the series, the sequence, I guess, as a function and then integrate over that, then you can compare the convergence of the integral with the convergence of the series. All right, so that's that one. Any questions about integral test? Cool.
I have a question. What did you say the three conditions were again?
Sure, yeah. So you always have to have that the series is continuous on the interval. The other one is that it has to be, well, it has to be non-increasing, which is really the same thing as decreasing. And then it has to be positive.
Okay, all right. Thank you.
You're welcome. Number 3 is the same thing. Show that the series n equals 1 to infinity 1 over square root n diverges by comparing it to the integral. So it kind of gives the answer away. It just wants you to see that it can also diverge. So just real quick, if I find the antiderivative here, the antiderivative of 1 over square root x is, I think it's just 2 square root x. We'll go with that. I'm pretty sure that's right. And then this is going from 1 to infinity. And then for this one, if I plug infinity into this, the square root of infinity is still infinity. And it's going to be infinity minus 2 when I plug the 1 into there, which is still just infinity. So in other words, it diverges. Since the integral diverges, this means the series also diverges. All right, so same thing as 2, but just the other solution. Are we okay with that? All right, moving on. Okay, so for these next ones, number 4 here, A through E, it's asking us to determine whether the following series converges or diverges, and then state which convergence test you used. All right, we'll start here at the beginning. So here we have the series n equals 1 to infinity, 2 to the negative n. I don't really like the way that one's written, so let's think about it more like this. 1 over 2 to the positive n. This is actually a series that we've seen before, but let's still talk about it. So let's just go through the tests to see which one's going to help us out here. The first test you almost always want to try is the nth term test. If you plug in n going to infinity into the sequence part, just the 1 over 2 to the n, it's going to go to 0. Whenever the sequence goes to 0, that means that the nth term test is inconclusive, so you just have to try something different. We have the integral test. We could try integrating over this, which we could do. It wouldn't be too bad. Other things that we could do would be comparison test or limit comparison test, so we could probably get away with one of those. And then ratio test and root test. Ratio test and root test work a lot. In fact, they probably work the most and are usually the easiest to use. I'm going to use the root test for this one just because we already have an n power. Remember that the root test is the limit of the nth root of the absolute value of the nth term of the sequence. All right, so plugging in what we have is going to be the limit of the nth root. I don't have to worry about the absolute value because 1 over 2 to the n is always positive anyway. And if I take the nth root of this, I'm just going to get 1/2. Remember that both the ratio test and the root test, whatever the limit comes out to be, we call rho, that funny looking p. And then depending on what this p is, tells us the convergence of the series. If the p is less than 1, which is what we have here, that means that we have absolute convergence. If the rho comes out to be bigger than 1, then it diverges. If the rho comes out to be exactly 1, then the test is inconclusive and you have to try something different. Okay, so that's part A. I used the root test and we got absolute convergence. Let's look at part B. All right, so part B, the infinite series 3 to the n over 2n factorial. I'll go ahead and say that anytime you have a factorial, you're going to have to do ratio test. There's not really much else that you can do to help you out. The ratio test is the limit of the absolute value of the n plus 1 term divided by the nth term. So for us, it'll be the limit of the absolute value. Because this is a fraction, I'm going to do that thing that we normally do by writing it as the n plus 1 term and then multiplied by the reciprocal of the nth term. So 3 to the n plus 1 divided by, and we have to be really careful about how we plug the n plus 1 into that factorial down here. So 2 times n plus 1 factorial, and I'm going to multiply that by the reciprocal of the nth term, so just 2n factorial divided by 3 to the n. All right, so again, the n plus 1 term multiplied by the reciprocal of the nth term. All right, and now we need to simplify this down. So we're going to use these tricks that I've shown you guys quite a bit at this point with the exponents and with the factorials. So first off, we have the 3 to the n plus 1, and I want to rewrite that as 3 to the n times 3 to the 1. It's going to be that divided by, so in that denominator down there, I want to distribute the 2 into the n plus 1, and then rewrite that factorial as 2n plus 2 times 2n plus 1 times 2n, and then I'll put the factorial. The other fraction I'm just going to leave alone because I already have enough stuff to cancel that stuff out. All right, so I'll re-explain this. So what we did is that the 3 to the n plus 1 I rewrote as 3 to the n times 3, that's using the product rule of exponents. We distributed the 2 into the parentheses here, that's going to be 2n plus 2 factorial. A factorial is just that number times the next number down, times the next number down, times the next number down, all the way down to 1. So 2n plus 2 factorial is going to be the 2n plus 2 times the next number down 2n plus 1 times the next number down 2n, and then that times everything all the way down. But we can just cut that off as 2n factorial. That way this 2n factorial on the bottom cancels out with this 2n factorial up top. Okay, now we can actually cancel some of that stuff out. The 3 to the n cancels out with that 3 to the n. We have this 3 left over in the numerator. The 2n factorial cancels out with the 2n factorial. So all we have left in the denominator is that 2n plus 2 times that 2n plus 1. So this is what we have left over after canceling everything out. We're taking the limit as n goes to infinity, and all of the n's are in the denominators. So that's going to make the denominator blow up to infinity, which makes the whole thing go to 0. Don't forget that limit is what the rho is equal to. Our rho is definitely less than 1, and whenever it's less than 1, absolute convergence. This time it's absolute convergence by the ratio test. So is that one all right? Part B here, any questions about ratio test? Okay, cool. Moving on, part C. The infinite sum, n equals 1 to infinity, negative 1 to the n cubed over n squared. So here we have this alternating part out in front. You could do the alternating series here and it would work out just fine. But I'm not even going to go to alternating series for this one. This one I'm just going to use the nth term test. Because if I look at just the sequence part, the inside, and I take n to go to infinity, because I have n cubed up top and n squared on the bottom, this is going to blow up to infinity. So by the nth term test, the sequence diverges, and thus the series diverges. Okay, so that was a pretty easy one. I almost think that there was like a mistype there, because that's a weird looking series. Let's move on. D. So the infinite series, n equals 1 to infinity, of negative 1 to the n over square root n. All right, for this one, if I try to do the nth term test here, because the n is in the denominator, if n goes to infinity, this goes to 0, which says the nth term test is inconclusive. We cannot integrate over this because of the alternating part. You could, if you wanted to, do ratio test stuff or root test stuff, but I'm just going to jump into alternating series test. I'm going to do an alternating series test because this is an alternating series. Remember, for the alternating series test, there's 3 things that you have to have. The first thing is that you have to have your use sub n's always come out to be positive. The u sub n's is the sequence, but without the alternating part. So just the 1 over square root n. This is definitely positive as n goes from 1 to infinity. So I'm just going to put a little check here. All right, 2. The next thing that you have to have is that you have to have your u sub n's be non-increasing. Or in other words, they have to be decreasing. This I'm also just going to put a check beside, because as n goes from 1 to infinity, the denominator is going to get bigger and bigger, which makes my u sub n's smaller and smaller. There is a more practical way of checking that, and that's by doing derivative stuff. If you take the derivative of your u sub n, and your derivative is always negative, that means you're always decreasing. All right, the last thing is that you have your u sub n as a sequence approach 0. And that's also something we definitely have. As my u sub n has n go to infinity, the denominator blows up to infinity, which makes the whole thing go to 0. So a check beside this one as well. So by the alternating series test, the above sequence converges. All right, is that all right? Does that make sense? Everybody okay with that? Let me ask you guys a question. If this alternating part was not there, would it still converge? So if we were just looking at the series 1 over square root n, does that converge?
It would not.
Right, it doesn't. Why doesn't it? Or what test would you use to see that it doesn't?
Oh, I just looked back. Didn't we already do that one? Wasn't that one number 3?
We did.
Okay, yeah.
Number 3, up here?
Yeah.
Well, yeah, okay, so yeah, I guess you could say that. So by the integral test, it doesn't. Yeah. Another thing that we could use here would be p-series stuff. So the exponent in the denominator is 1/2. And with p-series, as long as the exponent is bigger than 1, it converges. If it's less than 1, which is what we have here, it diverges. Since the exponent is 1/2, which is less than 1, the series diverges. So either way. Okay, moving on. E. So the infinite sum, n equals 1 to infinity, of 1 over n natural log n all squared. Just realized I can zoom. Maybe making things easier to see. Okay, so nth term test is going to tell us nothing. Comparison test might help us out. We could try that, but I usually stay away from comparison test stuff. Ratio test and root test might help us as well. But for this one, I'm going to do an integral test. I'm going to do an integral test because I'm pretty sure if I integrate from 1 to infinity, we can do the integral of 1 over x natural log of x all squared. there is something that we should check before we try to do this. That thing that we should check is we should check those prerequisites. These are definitely all positive, no issues there. It's continuous, except at 0, which is and 1, which may be a bit of a problem, right? If I plug 1 into this, natural log of 1 is 0, which calls an asymptote. You can fix that by just starting at a different location. Instead of starting at 1, start at 2 instead. It doesn't really matter where you start as long as you're starting at just a number and going to infinity. So I can't actually start at 1 because there's an asymptote there at 1. So I'm going to start at 2. The other thing that we need to worry about is we need to see if this is decreasing or not the entire time. I'm just going to do that by plugging this into the calculator and looking at the graph. So 1 over x times the natural log of x squared. I don't think I hit division there, did I? Oops. 1 divided by x times natural log x squared. Okay, and we'll graph it. All right, so here's that asymptote, like I was saying, at 1. But after that, starting at 2, it's definitely decreasing forever. So we're good. So we'll do this integral from 2 to infinity, 1 over x natural log x. We can do this with a u substitution. If I let u be natural log x, then du would be 1 over x dx, which would cancel out with this 1 over x dx. So now it's the integral. I'm not going to worry about the limits for now. Of just 1 over u squared dx, or du. This has antiderivative of negative 1/3 u to the negative 3, which, plugging back in the u and worrying about the limits now, let's write it like this: negative 1 over 3 times natural log x all cubed, not squared, cubed, from 2 to infinity. Okay, I did a lot there really quick. Sorry about that, but it was just doing the integral. So just a basic u substitution. Do the antiderivative of 1 over u squared, and then plug back in u, which was natural log x. And then I moved it to the bottom just because it looks nicer having a positive exponent instead of a negative exponent. All right, if I plug infinity into this, natural log of infinity blows up to infinity. It's 1 over that, so I'm just going to get 0. Minus, plugging 2 into that, I get negative 1 over 3, and then whatever the natural log of 2 cubed is. It's probably some awful looking number, and honestly it doesn't really matter. It's a number, which is what is important. So in other words, the integral converges. And since the integral converges, then so does the series. Okay, again, so we did the integral. The integral came out to be a number. Doesn't matter what the number is as long as it's a number and not infinity. And because the integral converges, we get that the series also converges. All right, so another integral test example. Everybody ready to move on? Number 5. Any last questions about any of these tests that we just did for number 4 here? A through E.
I have a question about, I think it was the alternating series test.
Yep.
So, it says the alternating series test, right? We have to meet those 3 conditions, right?
Yes.
What happens if it fails one of the conditions? Does it diverge, or is it inconclusive?
It diverges. Yeah, if it fails any of these, it diverges automatically.
Oh, okay. All right, thank you.
You're welcome. Good question. Nth. I don't know what you mean, Richard. Okay, so 5. Oh, you were telling me the test from a long time ago. That's okay, my bad. Number 5. Suppose you know that 0 is less than or equal to b sub n, these are sequences, is less than or equal to 1 over n is less than or equal to a sub n. And 0 is less than or equal to c sub n, less than or equal to 1 over n squared, less than or equal to d sub n for all n. Which of the series, A, B, C, and D, definitely converge, and then justify your answer? Alright, I really like this question. I think it's pretty thought-provoking and pretty neat. Let's start at the beginning, A sub n. So this is using comparison test stuff. The only thing that we know about A sub n as a sequence is that it is always bigger than 1 over n. So if you go back to the comparison test stuff where we had these inequalities with the sequences, you can kind of tell when stuff converges or diverges, whether it is bigger than something that always diverges or smaller than something that always converges. For the series A sub n, this thing is definitely going to diverge since it is greater than another series that diverges. Right? 1 over n is the harmonic series, which we know diverges. A sub n is always bigger than something that diverges, therefore it is also going to diverge. Alright, let's look at B sub n. What we know about B sub n is that it is less than something that diverges. What that tells us is nothing, not enough information. Just because you are less than something that diverges doesn't necessarily mean that you converge, but it doesn't mean you diverge either. Could be either way. Alright, the series C sub n. So with the series C sub n is always less than 1 over n squared, and 1 over n squared is a p-series that converges. Whenever you have something that is less than something that converges, it also converges. So the series C sub n converges since it is less than another series that converges. Alright, and then the series D sub n, just not enough information again. So D sub n is always bigger than 1 over n squared, something that converges, but just because you're bigger than something that converges doesn't really tell us whether it converges or diverges. Okay, so that's just using some comparison test stuff. 6. So question 6 is really the same thing as question 7. It's just that with question 6, I really break it down. And then question 7 is just using ratio test stuff to find the radius and intervals of convergence. All right, so let's go through this one real quick. So number 6, find the radius and interval of convergence using the steps below for this series. The series k going from 0 to infinity, 2 to the k over 5 to the k, and then x to the k. So a sub k represents the kth term. That's just going to be the series as it is. A sub k plus 1 represents the k plus 1 term, so that's just replacing all of these k's with k plus 1. Next is asking you to simplify the absolute value ratio of the k plus 1 over the kth term. So I'm going to write it as the absolute value of the k plus 1 term and then the reciprocal of the kth term. So it's going to be just 2 to the k plus 1. I'm also going to put the x to the k plus 1 up here in the numerator. And then the 5 to the k plus 1 would be in the denominator. That times the reciprocal of the kth term, which is going to have the denominator 5 to the k up top, and then the 2 to the k, x to the k in the denominator. All right, and we just want to simplify this down. And we've done this a lot at this point. So again, we're using powers, the exponent rules to simplify. Each of these k plus 1s is going to cancel out with one of the k's and leave a 1 left over. So it looks like we're going to have a 2x up top and then just a 5 in the bottom. So that is going to be the simplification. There's not really much else that we can do here. Maybe pull the 2/5 out of the absolute value, but there's no point in doing that. All right, down here, we're taking the limit of this simplification that we just got as k goes to infinity. But there are no k's that are left over here, so that limit just approaches what was inside the limit, that absolute value 2x over 5. All right, then it's asking us for the radius and the interval. To do that, we need a little bit more steps. Remember that this comes out to be the row, and what we're going to do is we're going to force that row from the ratio test to be less than 1. Whenever you have an absolute value is less than something, you squeeze it between the positive and the negative of that something. And then now we can multiply by 5 and divide by 2. We get negative 5/2 is less than x is less than positive 5/2. So this tells us what the radius is going to be. The radius is always going to be the halfway distance across your interval. The halfway distance in this case is going to be 5/2 because I go down to negative 5/2 and then up to positive 5/2. We have to be a little bit careful about the interval. This is going to be the interval. It's just that we don't know yet whether we should include the endpoints or not. And we find that out by plugging each of the endpoints back into the original series. So we're going to replace this x with negative 5/2 and with positive 5/2. I'm not even going to bother doing that though, because if I plug negative 5/2 into here, I'm just going to get negative 1 to the k, which is going to diverge. If I plug positive 5/2 into here, I'm just going to get 1 to the k, which is also going to diverge. So I'm not going to bother plugging in the limits because I can already see that both of the endpoints are going to diverge, which means my interval is going to be the negative 5/2 less than x less than positive 5/2. And then don't forget what that means. This means that whenever you do the series for this, this converges only on this interval of the number line. So if you were looking at the graph, then the series of this graph only converges on this tiny little space here between negative 5/2 and positive 5/2. Okay, and then the rest of 7, A through D, is just doing the same stuff, the same steps for each of these individual questions. I don't want to do every single one of these because it would just get kind of monotonous to do each of them. So maybe let's start with, I don't know, let's just pick one at random. Let's do C, because C looks pretty interesting. So if I try C, it's asking me to find the radius and the interval of convergence, which means you have to do the ratio test. With the ratio test, it's the limit of the n plus 1 term over the nth term. So let's do the ratio thing again. I'm not even going to bother putting in the alternating part because when you're inside of an absolute value, this alternating part just disappears. So I'm going to write this as the n plus 1 term, x minus 1 to the n plus 1. That's going to be divided by n plus 1 factorial times the reciprocal of the nth term, just n factorial, divided by x minus 1 to the n. Again, ignoring the negative 1 to the n because we're inside of the absolute value and it just disappears. So the n plus 1 term times the reciprocal of the nth term. This we're going to simplify down. that x minus 1 to the n plus 1, I'm going to rewrite as x minus 1 to the n times just x minus 1 to the 1. And then that x minus 1 to the n is going to cancel out top and bottom. I'm just going to be left with x minus 1 up top. For the factorials, I'm going to rewrite n plus 1 factorial as n plus 1 times the n factorial, which means the n factorials are going to cancel out, and I'm going to have an n plus 1 in the denominator. All right, so this is the left-hand part simplified down. At this point, we can take the limit as n goes to infinity. But notice that the only n that we have is in the denominator. If that n goes to infinity, it doesn't matter what my x is equal to, the whole thing goes to 0. Don't forget that this is that row. And since it doesn't matter what the x is equal to, it still goes to 0. That means that my radius is going to be infinity. And the interval of convergence is going to be negative infinity is less than x is less than positive infinity. In other words, this is an example of a series. Oops, didn't mean to do that. This is an example of a series that converges on the entire number line. Whatever this thing converges to, and we know it converges everywhere, not just on a small subset of the number line. Okay, but you would do the same thing for all of these other ones. Let's do maybe one more. Let's just do D. So again, it's asking us for the radius and the interval of convergence. We're going to do the ratio test. The limit of the absolute value. We're going to do the k plus 1 term. So just writing it all out. Times the reciprocal of just the kth term. We'll simplify this thing down as much as we can simplify it down. So my 3 to the k plus 1 and x to the k plus 1 is going to leave me with a 3x up top. This 2 will cancel out with that 2, but then I still have a k and a k plus 1 on the bottom. That stuff's not going to cancel. As I take the limit, as k goes to infinity, I have a k up top and a k on the bottom. As a ratio, these are going to go to 1, which means that the total limit is going to go to the coefficient 3x over the coefficient 1. So in other words, just the absolute value of 3x is going to be the limit of the ratio test. Again, we want that to be less than 1 for this to converge. And we're going to squeeze that between negative 1 and positive 1. Divide by 3, and we get negative 1/3 is less than x is less than positive 1/3. Automatically, that tells me that my radius is 1/3. We're going to have to do a little bit more work for the interval. So for the interval of convergence, we have to try the endpoints. Let's first try x equals, let's just do the negative 1/3. This is going to be plugging in negative 1/3 in for the x of the original series. So k going from 0 to infinity, still going to have that 3 to the k, still going to be divided by 2 to the k, but then it's going to be negative 1/3 to the k. All right, simplifying this down. The negative 1/3 to the k and the 3 to the k are going to cancel out to just be a negative 1 to the k. And we still have this 2k in the denominator. Okay. This, we have to decide whether it converges or if it diverges. This is an alternating series, so we can just use the alternating series test. I'm not going to write it all out. Let's just go through the three things in our head. If I ignore the -1 to the k, that means that my u sub n's is just going to be 1 over 2 to the k. Those are definitely always positive as k goes from 0 to infinity. Those are definitely, what's the next thing? Oh, decreasing. So as k gets bigger and bigger, this gets smaller and smaller. And then this definitely goes to 0. So in other words, this converges by the alternating series test. All right, so that endpoint we're going to have to actually include. Let's try the other endpoint when x is positive 1/3. So if I replace my x with positive 1/3, I get this. Again, the 3 to the k and the 1/3 to the k are going to cancel each other out. So we end up with just 1 over 2k. This diverges. It diverges because that's just the normal harmonic series multiplied by 1/2. It doesn't matter if you multiply by a number. Multiplying by a number is never going to stop something from diverging. So it still diverges since it is a harmonic series. All right, so finally, that means that we can write out our interval. Our interval is going to be -1/3, but including -1/3 to positive 1/3, not including the positive 1/3. I know that some of your homeworks, it stressed absolute convergence and conditional convergence. For this question, we have absolute convergence only on the insides. So just -1/3 less than x less than 1/3. But we have conditional convergence only at the location -1/3. Everywhere else it diverges. Okay, so radius and intervals, are we okay with using the ratio test to get those? Any questions about that? All right, so 2 last questions here. We'll probably just do one of them because they're really the same thing. So 8, find the nth degree Taylor polynomial for f of x is 1 over x plus 1 about x equals 1, include sigma notation. Okay, so anytime you're doing Taylor polynomial or Taylor series stuff, make sure you have the formula. So the formula is the series, n going from 0 to infinity. And then it is the nth derivative at the centering point A divided by n factorial times x minus the center A to the n. And then sometimes these are written with k's instead of n's. So this is just the formula. Make sure you have this formula with you when you go to take the Chapter 10 test and the final exam. The only calculations you really need to do is to figure out what the derivatives are up to n. Because this is generic, that means we have to come up with a formula for the nth derivative. So let's just start writing some stuff out. Initially, we have the function 1 over x plus 1, but I'm going to think of it as x plus 1 to the -1 because it's easier for me to do derivatives that way. We are also going to need to know what that value is at the centering point 1. So that's going to be 1/2 when I plug in x to be 1. Okay, and then the first derivative. So the first derivative of this thing, bringing that 1 down, taking 1 away. All right, this, if I plug 1 into it, is not obvious. Let's see. So that's going to go to the denominator. It's going to be negative 1/4, it looks like. So you can just plug that into the calculator if you're struggling with that. I struggled with it. The second derivative is going to be bringing that negative 2 down, leaving the inside alone, taking 1 away from the exponent. Plugging 1 into that is going to be positive 2 over 2 cubed, 8. So we get positive 1/4. Maybe one more, and then hopefully at this point we can see the pattern. So the third derivative is going to be bringing the negative 3 down, leaving the inside alone, taking 1 away. Plugging the 1 into the third derivative is going to give us negative 6 over 2 to the 4th, which is 16. So that simplifies down to be negative 3/8. Okay, so now we need to come up with a formula for the nth derivative. Every single time, what we do is we multiply the exponent down, and then we take 1 away from the exponent. It also alternates positive, negative, positive, negative. So let's go ahead and throw in that alternating term. On the even exponents, it's positive, so I'm just going to put an in. Another pattern that we have is that we have the coefficient 1, 1, 2, 6. You need to start being familiar with that. That's a factorial. So on the third derivative, we have 6 out in front, which is 3 factorial. So there's going to be an n factorial out in front. We also have the x plus 1, and that's going to be raised to, we have to be a little bit careful here. The third derivative has negative 4. The second derivative has negative 3. It looks like whatever derivative we're taking, it's the negative of that derivative minus 1. So negative n minus 1 as the exponent there. All right, this represents the nth derivative of our function. We also need to worry about plugging in the centering point 1 into this and seeing what we get. We're still going to have the alternating term in front. We're still going to have the n factorial. I'm going to put this other thing in the denominator. It's going to be a 2 to the n plus 1 power. So moving that to the denominator is going to make those exponents positive. And then, of course, plugging in 1 for the x is going to be 1 plus 1, 2. So that's where that 2 came from. So this represents the coefficient of the nth term at 1. All right, great. Now we can go back to the Taylor series. It's the infinite series. It's going to be the coefficient here. So just writing that out. That divided by n factorial times x minus the centering point to the n. What we can do here, which is kind of nice, this doesn't always happen, but it is for this question, is that I have an n factorial that shows up in both the coefficient and just generically down here at the bottom, so we can cancel those out. So we can still get the alternating part, we still get the 2 to the n plus 1 part, we still have the x minus 1 to the n, but at least the factorial stuff has disappeared. So this is going to be my answer. This is the Taylor polynomial for the function 1 over x plus 1. Most of the time, I'm not going to ask you to do the nth term. Most of the time, I'll just do, like, say, the 4th degree or the 3rd degree Taylor polynomial. Then you wouldn't have to find this nth term thing. You could just go up to the 3rd or the 4th derivative and write it all out that way. If we did want to start writing out the Taylor series, it would be the first coefficient 1/2 minus the next coefficient was 1/4, and then that's going to have an x minus 1 on it, plus the next coefficient was 1/4, But that's also going to be divided by 2 factorial, which is 2, so 1/8, and then x minus 1 squared. That's going to be minus, what was the next one? 3/8, I think? Yeah, 3/8. But that's going to be divided by 3 factorial, which is 6. 3/8 divided by 6 is 1/16. That's going to have x minus 2 squared on it. And then so on and so forth. Oop. So you can just write out the first few terms if you really wanted to. Oh, that's going to be cubed, not squared, my bad. X minus 2 cubed on it. Alright, so this Taylor series is exactly the same thing as this function on a certain interval around 1. Alright, and like I said, 9 is pretty much the same thing. Find the Taylor series. Okay, so that's Taylor series stuff. Is that one alright? Is there any questions about that one? I hope these are at least fresh in your mind because these are the ones that you guys were just doing this week. Any last questions about the test at all?
I haven't checked yet, but is there like a time limit on it?
No, there's no time limit.
Okay, all right.
Another thing is, as always, and a lot of you don't do this, which is disappointing. In Moodle, as you're working on it and writing out your notes during the test, make sure you upload your scratch paper into Moodle. It's very hard for me to give partial credit to those of you that do not upload the scratch paper, and I like to give a lot of partial credit for my tests. So I would highly recommend that as you're working on the test, actually write it all out on paper and then take pictures and upload that here so I can give you partial credit. The chapter 10 scratch paper thing. Next week, I do have a practice final and practice final solution, so we can start looking at that. But I would much rather focus on chapter 11 stuff next week, since you have homework due on the chapter 11 stuff. If you don't have any questions from the chapter 11 homeworks, then we can work on these final practice things. All right, last call. Any other questions about chapter 10? All right, cool. Well, let's end it here.